this video, we're going to talk about infinity. There are different kinds of infinity. There's countably infinite, and there is uncountably infinite. And we're going to talk about both these kinds of infinity here. Before we get started, we need to remember some terminology about sets. First of all, if a set is finite, then it has a finite size, and we can talk about how many elements are in the set. A set that is a finite might have, for example, 17 members, and we can just count the number of elements in the set. But when we start talking about sets that have infinite sizes, with an infinite number of members, we need to be a little bit more careful. So I want to remind you about this terminology if you haven't seen it before, or go over it if you have seen it. Let's assume that we've got a function f, and it maps elements from one set, the set A, to some other set, the set B. We call set A the domain, and B we call the range. So here you see a picture, and this is set A with some elements in set A, and this is set B. Okay, and F is taking each element in A and going to some element in set B. Now sets can act different ways on their domain and range, and we have these terms one-to-one and onto and correspondence. Let me go through each one of those in turn. First of all, if a function is one-to-one, what that means is that every element in A is mapped by the function to a different element in B. So here you see some elements in A, two elements in A, and they're getting mapped onto the same element by F. And that's not one-to-one. Okay? Here I'm saying it, and I'm using A and B, which is slightly confusing because here I'm also using the letters A and B. Perhaps I should say X and Y here instead of calling these things little a and little b. But if two elements are different, then when you apply the function to those two elements, you'll get a different element in B. If two elements are different, like these two elements, then when we apply the function to them, we'll get two different elements, elements that are not equal. So we do not allow something like this. We don't allow arrows to touch each other or their heads. Now that's one-to-one. Onto is something similar. In that case, we look at all the elements in the range. Remember, A is the domain, B is the range of F. And we look at all the elements in the range in set B, and we make sure that every one of them can be reached from an element in A. So we could say it this way. Every element in B is hit. There is an element in the domain that will correspond to the element in B when the function is applied to that element. We'll be able to get to that element in B. So we do not allow situations like shown in this picture. And finally, we can define a correspondence, and this is a picture of a correspondence. Any function that is one-to-one, in other words, these lines don't intersect, and onto, meaning every element of B is touched, then we have a correspondence. For every element in A, there is a corresponding element in B, and for every element in B, there is a corresponding element in A. So this function, if it is one-to-one and onto, it creates a correspondence between the two sets. Now we can start to talk about sets whose sizes are infinite. If the set has a finite size, then we can simply count its size, and if we can count the size of a set, then we know it is a finite set. But if the set has an infinite number of elements, we begin to have difficulties because we can no longer count the number of elements in the set. Georg Cantor came up with this very useful idea, which is to say that two sets are said to have the same size if and only if there exists a correspondence between them. In other words, if you can find a function that is a correspondence between the two sets, then we say that those two sets have the same size. So this is really a definition of what it means for two sets that are infinite in number to have the same size. And our second definition that's useful is we say a set is countable if it has either a finite size, for example, if it has 17 elements, it's countable, or if it's infinite and there's a correspondence with the natural numbers. Remember, the natural numbers start at 1 and go on up, 1, 2, 3, and so on. So we talk about a countably infinite set if we can put it into correspondence with the natural numbers. So here's the first example of this is the set of odd numbers. Okay, 1, 3, 5, 7, and so on. This set is countably infinite because we can put it into a correspondence with the set 1, 2, 3, and so on. In fact, let me show that correspondence. Okay, here are the odd numbers, 1, 3, 5, 7, 9, and so on. And here are the natural numbers, which I made with a little fancy N there. 1, 2, 3, 4, 5. And you can see there's a correspondence between them. Okay? You can figure out that function. It's a relatively simple arithmetic function. And so there is a correspondence between the natural numbers and the odd numbers. But also notice that the odd numbers form a subset of the even numbers. 2, 4, and so on are not elements of the set of odd numbers, but they are in the set of natural numbers. So we can have a situation where we have a set that has both the same size as the natural numbers and is at the same time a proper subset of the natural numbers. Now the next set we want to look at is the set of rational numbers. A rational number is a fractional number. Okay, that would include decimal numbers that have repeating digits at the end. For example, 0.3, which is really 0.30000, or 1/3, which is 0.33333333, etc. Those digits repeat. Those are rational numbers, and every rational number can be expressed as a fraction. 0.3 is really 3 over 10. 0.333 out to infinity is really 1 over 3. So a rational number can be expressed as a fraction, m over n, where m and n are both natural numbers. I suppose we should properly also include the negative rational numbers, which this doesn't include, but we can kind of ignore that for now. This set is countably infinite, and we're going to show on the next slide a proof that it's countably infinite. Okay, we're going to show a correspondence. And then the next thing we want to look at is the set of irrational numbers. Okay, this set includes numbers like pi and other numbers whose decimal expansion contains an infinite sequence of digits that does not repeat. So pi, the square root of 2, and so on are examples of irrational numbers. And there are also many, many more. In fact, we'll find out that this cannot be put into a correspondence with the set of natural numbers. So this set is uncountably infinite. I just said that the set of rational numbers is countably infinite. And in order to prove that, we need to find a way to put them into a correspondence with the set of natural numbers. In other words, we have to list them. We have to be able to create a list of every single rational number in such a way that every rational number is included. Okay, here I'm repeating the definition of the set of rational numbers. And I have left out the negative numbers, which, properly speaking, there are negative rationals as well as positive rationals, but we're just looking at the positives here. And so I need to come up with, in order to make this proof complete, a correspondence. Here I've shown the natural numbers 1, 2, 3, 4, and I've shown a few rational numbers. Okay? And so I'm suggesting the idea of a correspondence. And there's no system to what I've done here, and this is not actually showing a correspondence. It's just showing the kind of thing that I need to find in order to show that the set of rationals is countably infinite. But down here, I'm going to show a systematic way of listing every single rational number. I'm going to show a procedure for listing rational numbers, and that procedure will eventually list every rational number. And the order in which I list them will show the correspondence between the rational number and a natural number. So what have I done? I have made a table, and this table is infinite in both directions. So it's 1, 2, 3, 4, 5, 6, 7, ... and down here, ... And at every point in the table, I've taken the row number and divided it by the column number. So row 2, column 3 is 2 divided by 3, or 2/3. So if you give me a rational number, any rational number that can be expressed as m over n, and all rational numbers can be expressed as a fraction m over n, then it will be in this table. Okay? For example, if you ask about 17 450ths, well, that's going to be on the 17th row, the 450th column. Okay? It will be in this table. So this table is infinite in size, but as I start to draw this table, I will eventually hit every single rational number. Okay? If I want to draw this table, I'm going to start in the upper left-hand corner, and I'm going to go down and to the right at the same time, sort of the way I've done here. I'll never reach the right edge, I'll never reach the bottom edge because it's infinite in both directions. But I can just keep growing this table. And now that I know how to create the table, or at least a part of the table, I can start enumerating the rational numbers. So what I'm going to do is I'm going to go through this table on the diagonals, like I've shown here in this red line. Okay, and as I do that, I'm going to hit every element in the table. That's an infinite process, but I'll hit every element. Okay, if you pick some rational number like 17 450ths, eventually I will hit that number. I will hit every rational number eventually. And I'm going to list them out. Okay, the first rational number is 1 over 1. That's just equal to the number 1. So I print that out. And then I print out 1/2. And then I print out 2. I can simplify if I want to. And then I keep going, and I print out 3. And then here, 2 over 2 is the same as 1. And I've already printed 1, so I can skip that one if I want to. And then keep going. 1/3 I haven't printed out. Then I print out 1/4, 2/3, 3/2, and 4. And then 5 over 1. 4 over 2 is really the same as 2. I already printed that out. 3 over 3 is the same as 1. 2 over 4, I've already printed that one out. 1/5 I have not printed out. And so I print these numbers out. I print out the rational numbers in this order. This, 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 and so on. I keep going, and eventually I will print out every rational number. Any rational number you give me, I will eventually print it. This forms a correspondence, and this shows that the set of rational numbers is countably infinite. Okay, now let's look at the set of irrational numbers. It turns out the set of irrational numbers is uncountably infinite. There are many more irrational numbers than there are natural numbers. So what are irrational numbers? Well, we can represent these numbers with decimal expansions, and here I've shown a few examples. Our familiar pi, 3.1415, and so on. Really, these things have infinite decimal expansions, and they never repeat. So I should add the dot dot dots here. And I've shown square root of 2. Every whole number has either an integer root, its square root is either a whole number, or it's an irrational number with an infinite decimal expansion that never repeats. Likewise, the constant e, Euler's constant, is 2.7182, and so on, and that's an infinite expansion. And there are many more, and here's one I just made up. Okay, this is no number that anyone's ever thought about before. It's 5.679, and it's some number, with an infinite number of digits, and those digits never show a repeating pattern. Okay, now here are some rational numbers to look at in contrast. 1/3 is expressed in decimal as 0.33333, and oftentimes we draw a line over the last digit to say that it repeats. So in other words, it's 0.3 with an infinite number of threes. Okay, it can be expressed as a fraction, whereas none of these numbers can be expressed as a fraction of whole numbers. Now, between any two rational numbers, there's an infinity of irrational numbers. And I've tried to show that by showing a rational number, 1/3, and here's another rational number that's almost the same. It's very, very close, but at some point, the digits differ. Okay, in this case, I've drawn commas here to make it easier to parse, but in the 6th position, okay, this thing differs by 1 from 1/3. And then, since it's rational, it has to have repeating, and I try to keep it as small as possible after going up 1 digit here, so I use just zeros out here. So this number is a fraction. It's 333,334 1/millionths. That's the fraction that this thing is. It's very close to 1/3, but it's not exactly 1/3. It differs in the 6th position, and it has, like any rational number, it repeats. But between these two, I could squeeze in an infinite number of numbers. Okay, in this case, I am showing a number that is larger than 0.333333. Okay, it's larger because in the 7th position it's a 5, but it's smaller than 0.333334 because in the 6th position it's a 3. So, I don't list the digits out here, but you can see that between these two numbers there is a number that will fit in there. And I've suggested that there's an irrational number. Of course, there are rational numbers as well, but this is to show that between any two rational numbers, there's an infinity of numbers, and in particular, there's an uncountably infinite number of irrationals. So now, how can we prove that the set of irrationals is uncountably infinite? Well, the answer, or the approach to the proof, is to prove it by contradiction. Assume that there are countably infinitely many irrational numbers. So if there are countably many numbers that are irrational, then it stands to reason that we can put them in a correspondence to the whole numbers. So here I have drawn a correspondence. I'm using, first of all, I want to just look at the numbers between 0 and 1. So I've selected some irrational numbers between 0 and 1. The first one is pi divided by 10, right? 314,159. The next one is the square root of 2 divided by 10. And then e divided by 10. And then the number I made up divided by 10. And then some other numbers. Okay? But the idea is that any irrational number between 0 and 1 can be listed out. And if there are countably many of them, we can list them out in some order such that there's a first, second, third, fourth. There is some sort of correspondence. So we're assuming there are countably many irrational numbers. So if that assumption is true, which it is not, but if it were true, then we could make this table like this. And we could list these things in order, and we could put them in a correspondence with the natural numbers. Now the trick here to show the contradiction is to look at the diagonals. And so this is called a proof by diagonalization technique. If we look at the diagonals in this table, taking the first digit from the first number, the second digit from the second number, and so on, we can construct a new number. Okay? So what I've done here is I've added 1 to the 3 to get 4. I've added 1 to the 4. I've incremented by 1. In the case of 9, I subtract 1. In the case of 3, I've added 1, and I'm adding 1. The point here is I'm making a number that differs. Each of these digits differs from the corresponding digit in the diagonal. So this number is clearly not equal to the first number because it differs. The way I've constructed it, it differs in the first digit. And it's not equal to the number in the second number, 0.14142, because it differs in the second digit. And it's not equal to the third number because it differs in the third digit. And so on. And in fact, the number I'm constructing this way, which of course has an infinite number of digits, has a difference between it and every other number in the table. So this is a number that can't possibly be in this table. Yet this is a rational number. Yet this is a perfectly valid irrational number. So we've got our contradiction. Since this number is an irrational number, but it's not in this list, then we've got a contradiction because we said we were listing all the irrational numbers. So that is the proof that the set of irrational numbers is uncountably infinite.